Okay, clearly it's on. Well, so let's continue with our afternoon session. We'll have the second lecture by Ari Furman.
So I was talking last time a lot about how the entanglement depends on the size of a system, and I want to talk a little bit more about that, and then try to actually show that you can that the entanglement Hamiltonian makes sense. So let me first so I want to make sure something was clear. So I was looking at a region like this. I was looking at a region and a system, and you divide it into two regions, A and B. And I was saying the entanglement is short range. So the entropy of this region will only be contributed by the spins near the boundary. And that means the entropy of region A is proportional to the area. I said that, and then afterward I talked to someone who was like, oh, that wasn't very clear. So what I mean really is the entropy is proportional to whatever the size of the boundary. So if you're in 3 dimensions, the entropy is proportional to the surface area. And in 2 dimensions, it would be proportional to the length. And in 1 dimension, it would just be a constant because there's just 2 endpoints. So I could say entropy is proportional, if it's like a cube, it's the length of the cube to the dimension minus 1. I could say it like that. Proportional. So that's for a gap system. Okay, that was just to make it clearer. This is the reason why this is called the area traditionally is because this originally came up when people were thinking about black holes, and from Hawking and Bekenstein, they knew that a black hole had an entropy that was proportional to the surface area. And then they said, that's really strange. Why should the entropy be proportional to the surface area? Because entropy is usually, everywhere in a region, you have entropy, so it should be proportional to the volume. And then a explanation for that people thought of was that a black hole is it's like a wall, that you can't see anything inside of the wall. So if you think about quantum mechanics, if you cut off part of a system, you get entanglement entropy. So then maybe the entropy of a black hole is the entanglement entropy between the inside and the outside of the black hole. And that makes sense because entanglement entropy is proportional to the surface area. But I don't think anybody's ever figured out what it is that's entangled inside and outside. It's not like the gravitational field or something. You can't calculate it and get the right number, I think. But anyway, so that's where the whole idea came from. So this is for the ground state. And let's see, an interesting thing to think about is for an excited state. At a high energy. So by a high energy, I mean something like if you have a spin chain where the interaction is J, for adjacent spins, you have an energy that's on the order of J times the number of spins. Could be like a tenth of J, but it's like a finite fraction of J. So there's a conjecture about what states like that look like, which is that any state like that is basically a time average, because an eigenstate of a system, an eigenstate of a Hamiltonian, is independent of time. So you'd think so that makes it sound like since it's independent of time, it's like steady state. So anything that can happen at some time will evolve, and if you just start with the system and watch it evolving, any configuration you have will evolve into any other configuration if it's an ergodic system. But if you have a system that's time independent, which an eigenstate is, the only way that's possible is that it's sort of a superposition of all the possible trajectories that could happen in time. So there's a conjecture called the eigenstate thermalization hypothesis. that says if you have a chaotic system, like basically a generic system, then if you look at just a single eigenstate and take the expectation value of any operator, then it's the same as it would be in a thermal state with the right temperature. So with whatever temperature corresponds to the energy of this state.
Like local operator?
Yeah. So if, and why are you asking that?
I thought that trace is over the operator support.
Yeah. Or the trace is over everything. Like it's just the average. I'm taking the average in this ensemble, but
E to the minus H state resulting from trace now.
so, well, that's how you can argue. That's so. So let me ask your question for a different reason. So if I take this operator, so this can't be true for all operators, because if you take the operator to be the projection onto state psi, the left side of the equation has to be 1, because it's just the probability of being in state psi, and it's in the state psi. But the right-hand side is the probability of being in state psi, and there's many, many other states at the same energy, so that would be very small probability. So it can't be true for that case. Yeah?
What about the ground state?
So this is only true for higher energy states. This. Oh, I guess it's sort of obvious. It's kind of trivially true for a ground state, because for the ground state, if the t is 0, you do take the ground state expectation value. But so anyway, so this is only true for operators over a small region. So if you just take one certain spin, the expectation value, it'll be superimposed as much up and down as you would have in a thermal average. That's what this conjecture says. And I can rewrite it in a kind of a neat way. So if the operator is constrained to a region like A, then this expectation value is the same as, you can take the expectation value in 2 steps. You can first sum over all the possibilities for what the state of the system is in B, and then that turns the expectation value into the reduced density matrix in the region A, and then you sum over region A afterward. So it's easy to sum over region B because you don't have the operator in region B, so then it reduces to this. So this says that for any operator, this trace is equal to that. But if that's true for every operator, that means the density matrix just has to be the thermal density matrix. So that means that if we were to take the single eigenstate and then find the entanglement Hamiltonian for the region A, this would be the density matrix. So the entanglement Hamiltonian would actually be the logarithm of that, which is the real Hamiltonian. You get a slightly different one, but they'd be all approximately the same at these high temperatures, because each one is basically the same as the real Hamiltonian. No, I'm not saying it's trivially true. I'm just saying what it is, and it implies this. I guess so. I think people don't think of it. I mean, that's not the interesting case of it. So that's not really counted as part of the eigenstate thermalization hypothesis.
You haven't told us what the temperature T would be in general, but I suppose that depends on the energy.
Yeah. So the T should be T is equal, or T is such that expectation value of H equals, at temperature T equals the expectation value of H in the state. So you choose the temperature to make this work for that energy, and then it works for everything else too. So yeah, it would work. This formula works for the ground state, but it's not what the eigenstate thermalization hypothesis is about, kind of. So you don't usually think of that case. Yeah. Yeah. Well, T is, well, it's related to the energy in whatever way. Like you have an equation of state, or I don't know what you call the relation between E and T. You have like, if it's an ideal gas, you have E equals 3/2 nkt. So that's the relationship between E and T. Like whatever the relationship is for that system. I guess you think like in statistical mechanics, you say, let me solve for all the possible, like time independent, like probability distributions. And the only possibility is the Boltzmann distribution for some temperature. So the idea here is that this expectation value is given by the Boltzmann distribution for some temperature. And then you can find the temperature by looking at the energy and making sure you get the right energy. So, yeah. Oh yeah, that's I left that out a little bit. Yeah, this is really, no, in this formula it's the full H, but the rho A isn't exactly the full H. It is, the rho A would be, what's that?
The trace there is trace over A.
Yeah, and this is the trace over the whole system. So the entanglement Hamiltonian you get for A, you would get it by taking this thing and tracing it over B and then take the logarithm. So near the boundary it'll be slightly different than the real Hamiltonian. But away from the boundary it will be the same as the real Hamiltonian. So it is kind of, this entanglement Hamiltonian is like the Hamiltonian truncated, but not just straightforwardly. There might be some funny, you'd have to calculate it near the boundary. So the thing I think is very neat about this is if you look at, since the density matrix of the single state and the thermal density matrix agree, that means the entanglement, which is the entanglement of the state, which is just the entropy of the region A, that has to equal the thermal entropy at that temperature for the region A. So the entropy of this state, and entropy is proportional to volume, not to surface area. So the entropy of the state is actually proportional to the volume at a finite temperature. And that it seems kind of surprising. Well, I mean, it's not surprising that the entropy is proportional to the volume, but it's surprising that since the entropy agrees with the entanglement, that means the entanglement increases as you increase the temperature. And you always think like as you increase temperature, things get less and less correlated. But here it sounds like they get more and more correlated.
By temperature, you mean energy?
Oh, sorry, yeah, energy. Yeah.
Looking at higher energy later.
Yeah. Yeah.
Sorry, returning back to the trace, but when you're defining your operator
Yeah. But H has couplings between A and B. That's why it's a little bit non-trivial. Yeah.
But again, I'm missing something. So you're saying if you have, I can say something about this. This is the state.
Yeah.
But then from that it follows that the
Yeah, away from the boundaries. Yeah. So, and that also implies that the entanglement of a single eigenstate increases as you increase the temperature, which seems weird because you think at a higher temperature you should have less and less correlations. So does someone have an idea like why, where are those extra correlations coming from? Yeah, it's like you have kind of all kinds of excitations in the middle that are correlated to excitations out here. And they're probably also not even like single particle correlations. It's like you have 10 particles over here and their configuration is correlated to 10 particles over here, or a million particles, or very many. So you can't figure out, just by looking at a little part, you wouldn't notice that it's correlated to a little part here. It's only some combination of these whole particles is correlated to some function of these whole particles. It's like astrology. I'm sure there's some correlation between all the stars out there, but I doubt that any astrologer would, and me, and I doubt any astrologer would be able to figure out what it is. So it's not very useful. But it's interesting in this case, conceptually, I think.
But isn't there also some entanglement entropy because the state is going to include things like plane wave particles, where the particle is part of without some amplitude inside it with some amplitude outside.
Yeah.
And that's how.
Yeah. Yeah, I guess even if you don't have interactions, yeah, that's true. Wait, my notes are right here. Okay, so now I want to now I got to my notes. So I want to start to calculate the entanglement Hamiltonian for ground states, because it sounds like a very complicated thing to do. You have like a many-body density matrix, and you have to take the logarithm of that. So it turns out, at least for a for a relativistic system, the entanglement Hamiltonian you can calculate, even without solving for the ground state first, which is lucky because it's hard to solve for the ground state. And it turns out to be local. So I'm going to first give you a story of how to do it, and then I'm going to do it. The story is the fun part. So what we want to do is we want to take a system and cut it in half and look at the entanglement between the two halves. So one way, if it's a relativistic system, one way to cut a system in half is that you start running faster and faster at a constant acceleration. And then there'll be a part of the system you will never be able to get a signal from because light won't be able to reach you. So you can't outrun light, but that's actually not true. If you're accelerating all the time, then your trajectory is getting, if this is like time and space, your trajectory is going like faster and faster and faster and faster. And if the light started like far enough behind, it never catches up to you. Even though you can't actually get faster than the speed of light, you're always going faster and faster, and you're approaching it, and the light, it stays behind. So in this picture, you could never get a signal from any point behind this point. So by doing that acceleration, you cut the system in half at this point. And but then you might know, just have heard that, or you may actually know, that when you're accelerating in an accelerating reference frame, you see Hawking radiation. And well, I didn't mean to say that yet. So just by accelerating, you cut the system in half. And because the system is Lorentz invariant, your reference frame is independent of time. Like you're accelerating, but you're accelerating at a constant rate, so you don't feel any different. You're always constantly putting out the same amount of effort to keep accelerating. So you can describe your reference frame by a Hamiltonian. And that Hamiltonian is the entanglement Hamiltonian. Well, so it's not entirely obvious, but it makes sense because by going into that accelerated reference frame, you're cutting the system in half. So whatever describes the part of the system, the Hamiltonian that describes the system in your reference frame describes the system cut in half, kind of.
What do you mean? It looks like a thermal state with also wave that.
Yeah, so the next thing is you can say, the system, let's check that this makes sense. Because when we know from the quantum mechanics that it can't be a pure state if you cut the system in half. And then that agrees with what you know about Hawking radiation, because an accelerating reference frame, not Hawking radiation, like Unruh effect. Yeah, in an accelerating reference frame, you see radiation. You see a thermal, it seems to be thermal. And that's what we expect because we're looking at an entanglement Hamiltonian. So let me actually now derive it in a way that doesn't really sound too much like this, but it gives the same answer. So I want to calculate the log of the reduced density matrix. So I have to start by finding the ground state. So let me take the action. This S stands for action. Sorry. So I'm going to take that action, and then I'm going to go to imaginary time. Which just means you switch the sign of the sort of potential energy terms. So the ground state of a system you can get by doing the path integral. This is a nice way to represent the ground state. You do the path integral over a period of time from minus infinity up to 0. And so you integrate over all possible ways for phi to behave in the past, as long as it ends up at whatever value it is now. And that total amplitude is the probability. It's the wave function. So I'll fix phi at t equals 0 to be a certain function of t, a certain function of x. And then the path integral, I'll integrate the action over all possible configurations of phi before the time with this boundary condition. And that'll be equal to psi. That'll be the ground state. So that's just a nice, yeah. Oh yeah, this is d phi dx. Yeah, this is prime is d phi dx and that is dt. So now I have like a geometrical way to describe the ground state, and then I want to go from that to the density matrix. So to find the density matrix, I just say I'm going to trace over this half of the system. So that means I'm going to I'll split phi into two parts, like the left part and the right part. And then I'll set the left parts equal and sum over those because I'm not going to measure them. So I can just set them equal. This path integral is equivalent to the time evolution, like e to the minus h times all the time from minus infinity to now. So it just evolves it. Like any excited state gets suppressed much more than the ground state. So you get the ground state that way. So I'm going to just sum this over this. So I'm going to take the trace. Now I'm going to draw a picture for that. So I got one copy of psi is represented by integrating over negative time. And then I want to take another copy of psi, like the complex conjugate. So I'm just going to draw that. I'll just reverse. Since the action is symmetric in time, I'll just draw it up like that. So now I have two copies of the wave function. And I'm going to set the left-hand parts of phi equal to each other. So that means I'll just make this equal to this. So I'll make the wave function be not the wave function, the field be continuous across this boundary. But here I'm going to leave it uncontinuous. One side will be phi r and the other will be phi r prime. And then I integrate over all phi's satisfying this boundary condition. And that integral should be equal to the integral satisfying this boundary condition should be equal to the density matrix. So now I want to take, is there a question or anything? So like next I want to take the logarithm of that, so to find the entanglement Hamiltonian. So I want to write this as e to the minus he. And like an exponential is the same as taking some infinitesimal matrix and raising it to a large power. That's what the exponential is. So let me think, how can I write this density matrix as a small matrix raised to a large power? What I do is I just take, let me just redraw this so it's not as like ugly, like crummy looking. So I got, here's my phi r and phi r prime. And then this is continuous. And I'm just going, and I'm integrating over over this whole region. So now I'm just going to divide the region up into like sections like in a grapefruit. Many sections. And so if you do the integral over the whole system, you can get by integrating over a small region with certain boundary conditions, and then making them be continuous and summing, which is the same as multiplying matrices for each of these regions. So just the matrix that represents the transition from the phi, the amplitude for going from one phi here to another phi along that section, that's this. So this little section is described by 1 minus he over n. So, yeah. So that's a really good point. So the thing is, the matrices are all equal to each other because that's where I had to assume that's where I'm going to use the Lorentz symmetry, because the Lorentz symmetry, when you turn t into I times tau, it turns to a rotational symmetry between x and tau. So all these sections are equivalent to each other. Yeah, that's a very good point. So that means that actually all these HEs for each region is the same as every other HE. So now if I gotta look at the formula. So now I just take my Hamiltonian, or my action, sorry. And I just go into polar coordinates, because then like theta is sort of, you're doing a little bit of theta at a time, so it's good to do it in terms of theta. So in polar coordinates, d phi d tau squared plus d phi dr squared turns into just a gradient in polar coordinates. And then I'll just say theta is like time, because theta is the thing that we're sort of evolving, we're multiplying together segments for each little small interval of theta. So theta is like time, and that means this term is like the kinetic energy, and these are like the potential energies. So if I want to turn this into a Hamiltonian, I have to convert this into a momentum operator, which means I take sort of the mass, which is 1 over r, and take the reciprocal. So I end up with r phi squared over 2 plus r over 2 d phi dr squared So that's the Hamiltonian. Or that's the Hamiltonian, except I want to evolve for 2 pi units of time, so I have to put 2 pi in front. That's integrated over R from 0 to infinity. Yeah. Oh, I just kind of, like here there was like this big gap, so I just push them together. So then you end up with like a piece of paper with a slit cut into it.
And then does that correspond to?
Yeah, this is, maybe I should draw in, like, here's the slit, and then this is, I think this was the slit here. And then I took the piece of paper and divided it up into sections. So this figure here, I got by taking, this represents the wave function integrated over time from minus infinity up to present time. And then I take a complex conjugate of the wave function, which I'm writing as integrating from plus infinity down to the present time. And then I want to take the trace over the left side. So that means set the wave function, not the wave function, the field equal to each other, which means it's just continuous. And then so then it's like you've glued the piece of paper together, or you tape it together. That's my Scotch tape method for the day. On this section, and then you get a continuous piece of paper except for one slit. So you.
But there's no like when you do this kind of gluing with the density matrix without integrating out regions.
Mm-hmm.
You usually get two copies, like let's say Kelder's contour, you get 2 copies back, one from forward, one from side, one from side.
Yeah.
Here somehow is that why you go to the radial coordinates? Somehow you now looks like a single axis.
I guess so. I mean, this is the forward time, and this is like the backward time, but then they're connected together around that side.
What is the physical reason for the minus over x? Like you're doing
So this is, I guess, if you would calculate the exponential of the action, like an integrated over a small segment, you could write that as an operator applied to like the phi. You have phi on this side of the segment, and then you integrate this action between here, and you can write it as this operator. That's like the way the similar way is you just do a path integral for a particle and go from an action to like the Schrodinger equation. I'm just kind of guessing the answer because I'm saying, well, you just take the reciprocal of the mass and turn velocity into momentum.
having trouble with these pictures of the region.
Uh-huh.
That original goal
Oh,
is to calculate something.
I forgot. So I forgot to say what A and B are. So A is the right half and B is the left half. I should have said that. So I'm taking the trace over half this. I have a line, and I'm taking the trace over half the line. And then I get a density matrix in the other half. Or it's we're saying, say, if you're in one dimension. If you're in a higher dimension, you can do the same thing, and as long as you divide it by a plane. You can't do an arbitrary region. You can only do like a space divided by a plane into 2 regions. The rho is the density matrix of half the state. Yeah.
Sorry, so theta is like the time.
Well, in this mapping, you think of theta as the time.
Basically map it. So not theta doesn't match any time.
Yeah. Yeah, that's the tracing part. No, this is the ground state, what I'm calculating. Because the action integrating over that infinite time projects it to the ground state.
But the Hamiltonian is now sitting on that one slide, one radial,
Uh-huh.
connecting R and R prime. Where get the matrix with the operator.
Yeah. It's like when you, I don't know if you're like if you map the classical Ising model to the one-dimensional quantum-Ising model, you get a Hamiltonian. But here we're dividing it up into sections instead of lines.
Right, but it's non-locality. You know, the fact that it's local, but what I mean is it's the fact that it connects phi R and phi R prime. That's a big derivative. Phi d R. Exactly.
Or in phi d theta, I guess.
Phi d
yeah.
theta, which is phi phi.
Yeah, because that wants it to be continuous.
That's where we look at the matrix.
Mm-hmm.
That's the part that's the matrix.
Yeah. Mm-hmm.
Line up the calculation, the AT, I thought you were calculating some entanglement.
Well, this is, I'm saying that you can write this density matrix as a path integral like over theta, but then you can represent that by applying an operator many times, which means it's the exponential of that operator.
Relating rho,
Yeah.
I e to the minus u raised to the log to get AT.
Yeah.
That's entanglement.
Yeah. That's the definition
Now
of
you're
it.
saying it's just the action.
Well, it's not the actual Hamiltonian. I mean, it's very close, but it has that factor of R in it. So let's look at this Hamiltonian and try to interpret it. So that's a kind of a neat thing.
Sometimes it's called angular quantization.
Yeah.
I mean, if you think of the angle as a time variable, radial variable is spectrum,
Yeah.
quantized in those coordinates, the angle.
Mm-hmm. Yeah, think.
Sorry, so just to make sure I understand that comment, that's why we're
Yeah. Yeah. Yeah, that's, you're interpreting that as time. Yeah. So there's a very neat thing there's a very neat thing that you can get from this, which is that we've calculated, I mean, if we only had the ground state wave function, we could calculate the entanglement Hamiltonian just from the ground state wave function, because that's how it's defined. But then from this calculation, we see that the entanglement Hamiltonian gives you this time evolution in the angular direction. So that means you can actually calculate any correlation function in time that you want because you basically get all of space by just applying this entanglement Hamiltonian over and over again. So this is what people originally, this is called the, I should have written my notes. Bisagnano Figman theorem. And what they showed with this argument is that from just the ground state, you can get any correlation functions, which means you can find all the time dependence. So that's like what you sort of have a feeling like that's true when you're learning about particle physics, because you learn how the vacuum has all these particles and antiparticles, and like virtual uranium atoms breaking up into virtual boron and krypton and something. I mean, everything there is in the vacuum. So you sort of have a feeling that just from the vacuum you could figure out all the dynamics, and that's what this theorem says. You can reconstruct the dynamics just from the ground state and its entanglement.
So under what conditions?
Under the conditions that's relativistic. So that's why relativistic theories have to have quantum fluctuations, because they have to have enough information to reconstruct the dynamics in them.
But so this argument is intrinsically, you say, relativistic.
Yeah.
I mean, you couldn't do, well, what if you applied to non-relativistic? It would go wrong.
You wouldn't have the rotational symmetry. So each section would have a different like operator that describes it. And so then you would, when you combine them together, you won't just get the exponential of one infinitesimal section. Because the reason it's symmetric around theta. It's the same as relativistic symmetry. Because Lorentz symmetry is the symmetry between the space and the time. Like the Lorentz transformation turns into a rotation when you go to imaginary time.
I mean, the angle is the angle between tau and x.
Yeah, the rotational angle. Yeah. Yeah. Mm-hmm.
So I don't actually understand there's like
Yeah, but what I know is from the figures, I know that I want to do the time evolution in theta instead of in t. Because if you evolve in t, you'll get from one side of the cut and you'll never come back. But if you do theta, you'll come around.
So they've constructed the parking.
Yeah, it's from like 1976, I think. Yeah.
Assuming the original system is 2D.
It works also, if you think about it, it works in any dimension. The way I'm thinking about it is these pictures are for one dimension. But one space and one time dimension.
Can we see that the entanglement having to be in this one?
Yeah, that's what I want to do now.
It's not obvious.
Yeah, I mean, it still looks to be the same dimension. But so let's kind of analyze it. So you can see that it's the same as the real Hamiltonian, but multiplied by r. For this case, it's a little more complicated maybe for interacting theories, but that's the basic thing. And what that means is that as you go away from the boundary, this r times m squared is the gap. So the gap increases more and more and more as you go away from the boundary. So if you have a low energy excitation, it wouldn't have enough energy to get away from the boundary. And I can make it a little nicer if I write r equals e to the u. Then the entanglement Hamiltonian becomes, you have to change pi by a factor of r. I think pi goes to, because it's sort of like momentum density. So you have to put a derivative in there.
Not square root of u.
What?
Not a square root of u.
No, I think that's right.
2 over 2m.
I think because the commutator of pi with phi is a delta function, so you have to get the delta function. So, and I say r is equal to e to the u, so then I end up with du pi phi squared over 2 plus d phi du squared, but 1/2 d phi du squared. And then this term, I get r dr gives me a factor of e to the 2u. So the first part just looks like the free part, and the second part is like the mass, except that it's growing. I forgot the 2. It's growing as a function of the distance to the boundary. So here u is just the log of the distance to the boundary. So if we want to understand what that Hamiltonian means, we could imagine solving for the eigenfunctions of this wave equation, finding a wave equation and then solving for the eigenfunctions. And yeah.
What are the limits?
Oh, yeah, that's a good question. It's infinity up here, because r goes to infinity. And down here, it's r goes to the origin. So that would be basically minus infinity. But let's put a cutoff to make it a finite number. So if I would try to find the eigenfunctions of this, it's basically solving like a sort of Schrodinger equation in a potential that goes like m squared e to the 2u. So I get this potential. And the way that potential works is it's really small it's really small compared to the temperature, which is 2 pi, or it's 1, until e to the u gets on the order of 1 over m. And then once e to the u gets 1 to 1 over m, this increases exponentially. So basically at log m, at log 1 over m, the potential starts increasing really fast, and to the left of it, it decreases really fast. So you can basically think of this as a box whose size is just the distance from here to log a. So you get log 1 over ma is the size of the box. So then the entanglement Hamiltonian, basically, after you make this approximation, it's the same as the physical Hamiltonian, but just with a cutoff at the log of the correlation length. And that's really neat because
What's the correlation?
1 over m is the correlation length. If you would find the correlation function in real space, it would decay with the length of 1 over m. Yeah.
So on the left, so SE is
It's the Euclidean action.
No,
yeah.
here.
So that's my question. So
Uh,
on the left before you from S to SE just went to reversing.
Yeah,
Then you're saying
I should've.
from left before SE to the right before SE transformation, right?
yeah. I just changed the polar coordinates.
Yeah. So how do we know that this SE is?
But this, I shouldn't have said that. This is the Euclidean action. But here I actually mean the entanglement Hamiltonian. So, sorry. So I just said, I can do this time evolution as the exponential of a segment. So the matrix that describes that segment, that's the entanglement Hamiltonian.
So what did you do from the S?
I just basically, I did the same, like, when you're doing a Feynman path integral, you can figure out for an infinitesimal time what's the operator that describes how it evolves. And when you do that calculation, you find that the velocity squared gets replaced by the momentum squared, the momentum operator squared. So I just know that from that single particle case kind of, and I just wrote down the answer.
So I think we have Hamiltonian, then we constructed the Feynman.
Yeah.
So now you're saying this is just
Yes. Mm-hmm.
So how does that relate? How does that relate?
Well,
Like last this way you showed up from the infinity.
so this is, I want to,
He has a density
Yeah.
matrix that he can represent as a path integral, this radial path integral, or this angular path integral. And so that involves this path, this action, Euclidean action. And then you can write that as a trace of the exponential.
yeah, or the,
which
yeah,
is
the exponent.
By definition, the entanglement Hamiltonian.
Yeah.
Could I have just, skip the step of doing the slit your paper with a cut it into a cylinder?
Yeah. It just,
Yeah, that's good.
in the case, I guess since, like this also applies if you don't have conformal symmetry. So it's kind of nice, like the r equals e to the u is kind of an extra
Well, no,
thing at the end.
That's precisely what gives you the mass that grows, right?
Yeah. Yeah. That's true. But even with this, you can already see that it grows. It's just a little nicer with it. But yeah, but what I did do is you can say I did a transformation where I went from x and y to r and theta, so it opens up to a strip. Yeah.
So this also utilizes the fact that quantum mechanics
Well, I'm using the I'm using the path integral, which is sort of like statistical mechanics. I mean, I'm not really using that fact, but it like helps me to think about it. Yeah.
There is of course a what is called a canonical procedure, classical mechanics, field theory, thing called action.
Yes.
That's what you actually
Yes.
use.
That's what I.
You don't have to mention path integrals or no path integrals.
Well, to know that I got the ground state, I'm representing it by a path integral.
Sure, I know.
Yeah, but this last step is just canonically quantizing it. Yeah.
No, not even that. It's going from Lagrange into Hamiltonian.
Yeah.
That's all.
Yeah.
Whether it's classical or quantum.
Yes. So, now where am I? Oh, well, then it just looks nicer. Well, then, I mean, I could say one part of it comes exactly the same as the real Hamiltonian. So that's nice to see that it's almost the same as the real Hamiltonian. So now I'm going to let me apply this to find the entanglement entropy. That's part of the answer to your question. So my entanglement Hamiltonian is the same as the real Hamiltonian for a certain length, and then it just kind of ends. So that would mean that the entanglement entropy, which is the entropy of the which is like the thermal entropy of the entanglement Hamiltonian, that should just be the same as the physical entropy, except in a finite region, in a region of the length 1 over ma, and at a temperature of like 2 pi, 1 over 2 pi. Sort of. So now I know that the entropy, if you have the entropy of like a free scalar field is equal to, I don't know what it is. It's equal to pi times the temperature over 3 times the speed of the waves, which I hear was equal to 1, but generally it's pi t over 3v times the length of the system. So that means the entanglement entropy is just the same thing, except that I replace the length by the logarithm. So the entanglement entropy is equal to 1 over 6. The velocity is equal to 1. And I get log of 1 over ma. Or I could also write that as the logarithm of the correlation length over the cutoff. So, and this whole argument works. So the basic idea is the entropy is proportional to the logarithm of the correlation length, because the entanglement is proportional to the log of the correlation length, because it's the entropy of this system, and this system ends at the log of the correlation length. It's a finite system. So, and this actually works for any conformal theory, because this transformation from x and y to u and theta is a conformal transformation. So the conformal part of the Hamiltonian just never transforms at all. It just stays the same in the new variables. And then you have another term that gives you a finite correlation length. So you always have the entanglement entropy is whatever the physical entropy is in the units of t over v times this logarithm. And that proportionality between the entropy and t over v is called the central charge. So that's the fact I told you, that just from the entanglement entropy you can find what the specific heat is.
This is you start out with a gap system.
Mm-hmm.
So what you're finding is just the entropy is just defined with the correlation length of
Yeah.
thickness of the
Yeah.
just the area law technique. Okay, but it's the log.
Yeah, it's the log.
It's the log.
Yeah. But that's, if you want an even more qualitative result to this, it's that the system, the only place that you can excite things is between this this region and the correlation length, which is our intuitive picture at the beginning, that the entanglement Hamiltonian is localized near the end of near the edge of the region. Yeah. Oh, C is it's the physical. Let me write the general formula. The physical entropy is the real entropy is defined as pi ct over 3v, where C is the central charge, which that's like the definition of the central charge.
Yeah, like a physical picture. So like if it was, I guess, not conformal theory, then I would just say the length of it. It would be just a it would be just a correlation. It would be T times the correlation length.
Yeah.
Exactly this formula you wrote. S is T times the length.
Yeah.
But through this
Why is it the
transformation,
logarithm you're saying?
yeah, so like just to get some feeling, why is it you double the thickness of the, the
Yeah.
correlation length, but it doesn't change much?
Well, I think it's because like the things near the boundary are correlated very strongly, and as you go farther and farther away, they're still entangled a little bit until you get to the correlation length, but they're mostly entangled with things on the same side of the boundary. Like the amount of correlation with the amount of entanglement with the exterior decreases. I guess like 1 over x. So when you integrate 1 over x, you get the logarithm. I mean, I made up the 1 over x to get the answer, but it makes sense. It makes sense that it decays as you go away from the boundary. Because like within the correlation, you don't have perfect correlations over the length c. You have like less and less correlation.
Oh, I see. 1 over x times that times correlation. That falls out. So as long as you're within the, you're saying as long as you're within the correlation line, there's still some fall off.
Yeah.
Okay.
Yeah.
Which is the conformal, conformal field theory. The
Yeah.
fall loss associated with the mass.
Yeah. So you get the 1 over x from this transformation. But yeah.
So is it because the correlation length is shorter, or because it's hard to get culture?
Yeah.
I thought it's probably because of that very hard. It's hard to make culture because of barrier.
Well, like the smaller the smaller the mass is, the longer the correlations last. So you get like more entanglement if you have a smaller mass. And the reason for that is like if you have a big mass, it's really hard for things to fluctuate. So it's also hard for them to get entangled because they're just like frozen. Oh, space. I'm thinking in space. I meant space. Yeah, over a long distance. So let me see where. Yeah. Yeah, at a finite temperature. Yeah. Well, this entanglement Hamiltonian is a density matrix at a finite temperature. So then I don't have to worry about the eigenstate thermalization because I have a density matrix. I don't have a pure state. Let's see. I think I guess I'll ask you for a vote of what, or I don't know about vote, but like, are you interested to see like an application of how you can measure kind of experimentally using like fluctuations of density? You can sort of measure properties of the entanglement Hamiltonian. Or the other thing I could talk about is using entanglement to like recognize topological phases. But I think I can't do both.
Can we raise our hands to vote?
Okay, sure. Uh, who wants to see the topological thing? Who wants to see the other thing? Kind of equal. I think I do the topological because it's like a different feeling. It was weird because it was very, depending on where people were sitting. It's also good to do the topological stuff because then I get to use the pictures that I drew. See these beautiful pictures. Actually, I don't. Oh yeah, I guess I do get to use them a little bit. I don't know actually. I think you can look at them, but I don't think I'm going to use them actually.
Yeah, which one is this? First one or second?
This is the tensor networks, but I don't think I have time to explain the tensor networks.
Well, you can follow Nick and Jake on it.
But I'll just say it. I'll try to say it quickly what the tensor networks are. So this is something that's a useful concept for numerics. Like Stephen White's going to talk about, I think, numerics on spin liquids, and the method he uses is based on tensor networks. So I'll just say quickly the idea of it. So like the idea is it's hard to describe a many-body state because it's a superposition of all different configurations of many particles. So if you just define it term by term, you'd have to look at each combination of spins and then say the amplitude of that. But intuitively, you feel like each particle is just correlated to its neighbors, so there should be a more local way to describe a state. And the idea of a tensor network is it gives you a way to construct a state in a sort of local way. So the way you do it is you imagine you have some particles, and I'll call the particle, and I want to describe a wave function of the particles. So I'll call the state of my particle T and S and M for no reason. That I just thought of those letters first. And I'll say T goes from 1 to whatever the dimension of the Hilbert space of this particle is, and S goes from 1 to some other dimension, M goes from 1 to some other dimension. And I want to describe a state where these three particles, or more, I could add more, are entangled with each other. So the way you do it is kind of a strange way. You start with this particle, you combine this particle with a few other particles, and you make some entangled wave function out of them, which looks silly in this case because this is already 4 particles, and we only wanted to describe 3 particles. But the point is, if you have many, many particles, yeah, now it's working. I don't know what happened. So this one's working too now.
I think the battery
College clarification.
Maybe I just, does that work? So so yeah, it's okay. So I'm gonna now, I want to get T and S and M entangled. And I have to be really careful because I want to get them into a pure state. And that means I have to get rid of these red particles without leaving any entanglement behind. Otherwise the T and S and M will be in a reduced density matrix. So what people do, like the idea is you take the corresponding particles after you put each group into its state, and then you look at the corresponding particles like alpha 1 and alpha 2, and you measure whether alpha 1 and alpha 2 is in this state that I'm about to write or not. So this is sort of like an EPR state. You have two particles that are in exactly the same state, but it could be any state. So I'm going to take these two particles and measure if they're in this state or not. And I'm going to do the same thing for the two betas and the two gammas and the two deltas. And if any two of them are not in the right state, then I'm just going to throw it out and start all over again. But if they all come out in the same state, then T and S and M will become entangled because T was correlated to alpha. And now I know that alpha 1 and alpha 2 are in the same state. So now T and S are correlated. And the only extra thing you have to check is that T and S and M aren't entangled with these ones, because otherwise you'd have an entangled state for everything. And that's not what we want. We just want a wave function for these three particles. And does someone know why the T and S and M aren't entangled with the red particles? If this measurement succeeded in each case? Yes. Yeah. So the alphas are in definite state. So if part of the system is in a definite state, then the remaining part is also in a definite state. What's gamma? Like these gammas? Oh yeah, you do this for each pair. You do it for alpha 1 and alpha 2. And you do it doing for gamma 1 and gamma 2 gets M and T correlated and so on. So that's just I wanted to describe it that way because it kind of gives you an idea physically what you're doing. And you can see it's kind of a crazy thing because if you had many, many particles, on the one hand it's nice because it's a local thing. Like if these particles are, say, like arranged in a grid or something, and I'm only comparing the alphas that are nearby, then it's like I first created some small entangled state, and then I did a local measurement, and now I have the state that I want. So it's simple in that way, but the problem is there's only a chance of 1 out of d squared that this will work in each case. So it's a very small chance that if you have many, many particles that you'll get the state that you want. But that's conceptually the way it works. If you want to see it mathematically, which is a lot easier to understand probably, you represent each of these wave functions. You think of it as a tensor. So basically, I make a network with these blue dots connected by line segments. And then the physical degrees of freedom, like the T and S and M, I connect them to the blue dots. And if I want to calculate, so that picture represents the wave function. And the way I get a wave function out of it is I say, suppose I want to know what psi is when T and S and M are each 1. Then I put 1 here and here and here. And then I take this tensor, which is this chi has 1 index for each line coming out of it. So I replace the M index by a 1. And then all the red indices each appear twice because there's 2 tensors. So I just kind of I multiply all these tensors together, and then I follow the Einstein summation convention. I say beta is repeated twice, so I'm going to sum over it. And then I end up with the product of these tensor is contracted, and I get the value of the wave function for this particular value of t and s and m. So let's look at an example. For the toric code state, if I want to describe the toric code state by a tensor network, actually I'm not going to do that because that's a kind of that's a neat thing, but it's not. I can't go anywhere with that. So what you can do, let me look how you describe a one-dimensional system using a tensor network. So if I have a one-dimensional system, which is a sequence of particles, where the first one is in the state I1 and the second is in the state I2 and so on, you have maybe you have an infinite number of particles in both directions, actually. You can make a wave function for them by making a tensor network where you have a gamma with 3 indices, and that's connected to a lambda with 2 indices, which is connected to a gamma with 3 indices, and so on. And you multiply them all together, and then you sum over the repeated indices. And that gives you the value of this wave function. So the thing that's neat about this is if I have an infinite system, I don't really need to have an infinite, a wave function of an infinite number of variables. I just need one set of gammas and one lambda matrix. I call in gamma a set of matrices because you could sort of think of it as if this line index you call alpha and this you call beta, it's like gamma I alpha beta. And then when I multiply these together, I'm contracting the beta of this one with the alpha of that one, which is just like multiplying the matrices. So if you have a spin a half, if these are spin a half particles, you just have a gamma up matrix, a gamma down, and a lambda. You don't really need lambda, but I'll say why you put it in a second. Yeah. So this is a wave function. And you can think of it as contracting the tensors, or you could also think of it as basically, if you want to know the amplitude of a given configuration of spins, you take a matrix, a different matrix for each spin up or spin down state, and then multiply them all together. The lambdas are like, they're not connected. Yeah, it's different from that picture. They're not connected to the environment at all. So one other thing that's neat that I can do with this is I can see what the Schmidt decomposition of this state is. Because suppose I want to cut the system in half here. I can think about the sum over. To do that, I'm going to think about summing over these two indices here, alpha and beta. And so I'll fix those indices, and then what I have left on the left side is this wave function, and on the right I have this wave function with the fixed value of beta. And then I have to multiply that by the value of lambda and sum over alpha and beta. And then if I just call this wave function alpha, and I call this part of the wave function, and this part of the wave function I call beta, then I just have sort of a Schmidt decomposition, except that lambda isn't diagonal yet. And it turns out you can always represent a matrix product state by transforming gamma and lambda the right way. You can get an equivalent wave function where these alphas are orthonormal and the lambdas are diagonal, and then that gives you the Schmidt decomposition. So that's a neat thing. Yeah, that's a good question. So if you'd have to stop somewhere because you do. And when you stop, you can just you just fix whatever index you like at each end. And the thing is, as long as it's far enough away, if you calculate expectation values, it'll cancel out. Like if I take the expectation value of an operator over here, this is so far away that it doesn't influence it. So you have to fix the boundary conditions to calculate it, but then it cancels out in the end. you'll actually now you can sort of see why a little bit in the next example. So, I just wanted to define this. Well, I wanted to define this, show that you can make a large, like a one-dimensional wave function just out of sort of points, like small objects, and construct the whole wave function. Yeah. Yeah. Well, this class of wave function is nice because you can actually like numerically you can find the Schmidt decomposition. It's easy to calculate the overlaps of the alphas in this representation, and then you can do the singular value decomposition. Because if I describe the wave function as just a many body wave function, it would be exponentially big. Oh, because the lambdas turn into the Schmidt weights. Yeah. Yeah, otherwise you can just combine it with the gamma. But it's nice to leave it out. So now that I did this, I want to sort of see in another way that the entanglement, the different states of the entanglement spectrum are only different from each other on the boundary. Like the low energy degrees of freedom are near the boundary. So I'm going to look at the Schmidt states to the left of this segment. And I want to take the expectation value of some operator and see that expectation value approaches the bulk value as the operator moves away from the boundary, independently of what state you're in. Oh, I didn't say, there are conditions. There's some pretty simple conditions that make them orthonormal on these matrices. So now to calculate suppose I want to calculate the expectation value of an operator. Let me explain this figure. There's a figure you can use to calculate it, and I'll explain it. I take the wave function and I write it down here. And then I want to multiply it by the complex conjugate and sum over all the states of all the sites except for this operator, except for the one where this operator is acting. So this represents the wave function, and this represents the complex conjugate. And then when I sum over the state, I have to set them equal to each other and sum it. So I just connect them by a line, which automatically makes them the same value in the way this notation works. And then to put this S operator in, I just put the S in on this leg. So this gives me a picture of what the expectation value is. And then I just want to divide it by the normalization of the state. So and now the neat thing you can do is you can, just like when you're solving one-dimensional statistical mechanical models, you can use a transfer matrix. So I can think of this rung of the ladder as being a matrix that transfers you from this pair of bonds to that pair of bonds. And this rung transfers you from this pair of bonds to that pair of bonds. And once you do that, if I call these matrices T for the regular rungs and T of S for the one with the S on it, this expectation value will just be equal to T to the N, because you have N, you have to apply it N times till you get to this, times T of S, and then you apply however many you need to get to the end of the system, like N minus N. And then I just want to calculate the matrix element from the initial condition to the final condition, whatever the final condition is. And when you calculate this, if this N is a large number, this T to the N just becomes a projection onto the highest, whatever the largest eigenvector with the largest eigenvalue is. So you just end up with basically this approach is T of S, like sandwiched between the largest eigenvector of T, and it's the largest left eigenvector of T and the largest right eigenvector of T. So independent of n, because all that, once n is large enough, you just project to the highest eigenvector, and then there's no more dependence on n. There's an exponential, there's a power of that eigenvalue to the nth power, but that cancels out. It's, well, you can normalize it so that it's 1. Yeah. But, or yeah, if you divide by this, then the numerator and the denominator have the same factor. Yeah. So like, in the remaining 10 minutes, well, that's as bad as I thought, actually. I want to like think about like topological states in 1D. So like, let's try to understand. So the problem that we're talking about is, like in general, when you're talking about topological phases, is you have a phase diagram of all possible everything that the world can be. You have a bunch of axes that represent like the types of atoms and the distance between the atoms, and maybe they're not atoms, maybe they're quarks or whatever. You just put a ball in, make a lot of axes, and then you take this region and you color out, you draw in white all the regions where it's gapless. I'm gonna kind of take the problem and make it a geometrical problem. So you have like all different regions that are separated out by the white regions, and the phases are the connected components. Imagine if you cut out the white spaces, it'll break up into different pieces, and the different pieces are the phases. And it's a tricky thing because you might have a region over here that has like a little tube that connects it to some region over here or something like that, and then they would count as the same phase. So for an experimentalist, they may look at a cross section like this, and they may not care that this phase is actually the same as that phase, because they're not going to like mix in some quarks, which is what you have to do, or something to get it to turn to other phase. They're just going to look at a specific axis. But conceptually, it's an interesting problem to understand what are really all the possible like connections you can make between different phases. So as an example, let's look at the phase diagram of just a spin 1 chain, where I add an anisotropy term. So, and I'll fix j to be a positive number, and then I'll just look as a function of u. And it turns out like when u is equal to 0, you have this gap state according to Haldane's conjecture. And above, when you increase u enough, if u is very large, you can ignore this term, and then just every spin wants to be in this SZ equals 0 state. So at first you might think that there doesn't have to be phase transition, because in the Haldane state, you have, it's like an antiferromagnet, but there's so much quantum fluctuations that the average of the spin equals 0 in the Haldane state. And in this state, the average of the spin is also equal to 0, just in a trivial way. So they seem to have the same symmetry properties. But if you would numerically like find the ground state from along this line, like using this DMRG method, for example, you find that the gap goes to 0 at a certain point. So then the question is that like an accident, like maybe the transition from a water liquid to water vapor, and like maybe there's a way to connect them to each other, or is there actually a difference between the two phases? So there's no order parameter for this because in all the phases, the expectation value of S is equal to 0. I mean, there could be a more complicated order parameter that I just didn't think of. But at first, it seems like there's no order parameter. There's actually, with these tensor networks, there's a systematic way to check if there's an order parameter. But there's no order parameter. So what changes between those two phases? Like, is there anything that changes? And if you do it with the with the DMRG, then you automatically get those lambdas. And those lambdas are just the Schmidt eigenvalues. So I can graph the Schmidt eigenvalues for each state. And for this state, you find the Schmidt eigenvalues all look like two lines together with like different spacings. They're all like on top of each other, pairs of lines. And then the other state, there's sometimes a single line and sometimes a double line. Like that. So it kind of looks like the symmetry change because you think of multiplets as coming from symmetry. But both states have the same symmetry. So what happened? So you can see that this is a good thing to look at because we can actually see a difference between the two phases in the entanglement spectrum. And now the question is, can we understand why? So that we actually can say more than just that the entanglement spectrum is different. So what you can do is let's imagine we take the spin chain and we divide it up into two regions. And this time I'm not going to cut it in half. I'm going to cut a section out, a really long section out of the whole chain. And then I'll look at the entanglement between this segment and the environment. And so I'll have like a bunch of different eigenfunctions, Schmidt states of that segment. And what they all look like is they basically, near the edge, they have some pattern of spins. But in the interior, the spins get really small. The average value goes to the bulk value. So the only difference between these states is on the edge, which is what I was calculating, or sketching how to calculate just now. So what that means is if I take one of these states, just call it like, I'll call it alpha beta because you can sort of think of describing each endpoint independently of the other endpoint. If I take this state and I look at the symmetries of this Hamiltonian, and the Hamiltonian has a symmetry around the z-axis and also 180-degree symmetry that flips the z-axis to minus the z-axis. So if I take one of those symmetries, like RZ, let me just rotate 180 degrees around Z. I'll get back the same state in the bulk, because in the interior of the segment, the effects of which Schmidt state you choose have decayed. So I get the same state in the bulk, but there'll be some changes on the ends. And because the ends are so far apart, you can just treat them independently of each other. So I can write this RZ as a matrix, as an operator on the left side times the operator on the right side, times this alpha beta. And I'll just call this UZ and VZ because it's associated to this rotation. And this factorization is going to help us understand why there's a degeneracy. But one thing that's tricky about it, which is important, is that if I just add that it's not unique, this factorization, because I could add a factor of e to the I alpha times UZ and a factor of e to the minus I alpha times VZ, and I'd still have the same product for any phase. So it's unique up to a phase. And that's important because if I now take my other rotation, like my 180-degree rotation that flips the z-axis, and I factor that as ux times bx, the relationships between the u's can be a little bit different than they are ordinarily. So what I'm going to look at is, I'm going to look at the following relationship between these two rotations. I'm going to check whether these two rotations commute. And then I'm also going to, argue that they might behave differently in terms of the u variable, in terms of the u operators. So I want to check whether these commute. Leo, can I borrow your computer? Or are you in the middle of? Oh, that's good. Well, I don't need the computer part of it. I just need the object. So, where's, okay. I could use them both. So I want to check that whether these rotations commute or not. So I'm going to define Rx to be the rotation around this axis, and RZ is the rotation around this axis. Oops, I did it 360 degrees. But I want to just do it 180 degrees next time. So to check whether they commute, I'm going to do one, then the other one, and then I'm going to undo them, but in the same order as I did them. And if I get the identity, it means it commutes. So it's like if you want to check whether taking your shoes off and taking your socks off commute, you take off your shoes, then you take off your socks, and then you put it back on your shoes and you put back on your socks, and you see what you get. So those don't commute. So, oops. Yeah, then that would not commute. So watch carefully to make sure I actually do the inverse and not at the times that I'm supposed to do it. And also remember the way it starts out. But luckily we're provided by this lovely Apple logo from the Apple company, so you can tell. So I'm going to rotate 180 degrees around X, and then 180 degrees around Z, and then I'll undo X, and then I'll undo Z. Did it commute? Yeah. But were you watching carefully, Leo? Can you? No. Oh, you were too worried about that. I'll ask Victor instead then.
No, I'm kidding.
Well, but maybe Victor wasn't so worried, so I'll ask him. Did you notice whether the sign of the wave function changed or not? Oh. Yeah, so it came back to itself, but you never can tell about the phase of the wave function just by looking at the object. So it turns out that for an integer spin particle, you can tell whether there's an even or an odd number of electrons and protons and neutrons in it by checking whether the sign changed or not. Because for bosons, it comes back to the same, and for fermions, it flips the sign. Yeah, you can't actually, yeah. But so in this system that we start with, it's made out of spin 1 atoms. So they actually commute. You can just check with the matrices actually. That's more practical, that they commute. But then if I look at the U's and V's, the phases of the U matrix are not well defined, or they're not uniquely defined. So it might be that, like, if the R's commute, it means the U's have to commute, but only up to a phase, because whatever phase you have left over could be canceled out by the V's. So this implies that UX and UZ either commute or anti-commute. Like plus or minus one. Oh, it implies that you get a phase, but then you can think a little bit more and say that because UX is the order 2 transformation, it has to actually be plus or minus 1. So this is what distinguishes the phases actually. So we start out with the system where Rx and Rz commute, but then when we look how this symmetry acts on the 2 ends of the entanglement spectrum, they may actually commute or anti-commute. And if they anti-commute, it really means they anti-commute for every state in the entanglement spectrum, because otherwise this wouldn't be just a phase, and that would mean that this wasn't a symmetry of the Hamiltonian. Yeah. So that's using this uses the idea that in the low energy states, the bulk is basically nothing happens in the bulk, so you only have to transform the ends. But yeah, the low entanglement energy. Yeah, if you have a finite length of segment, the longer the segment, the higher you'd have to get before it splits. But it's spread out from the end, like it takes a high energy to get them to spread all the way to the middle. So actually, this is also the spectrum only for one end. So you get a fourfold degeneracy if you include both ends together. So the reason you have a degeneracy is because if you have two anti-commuting matrices, it means every energy level. These two matrices anti-commute, and they also commute with the entanglement Hamiltonian, because they're symmetries of the density matrix. So that means they commute with the entanglement Hamiltonian. So that means for any energy level you can find another one by applying ux and uz. Or you could simultaneously diagonalize the entanglement Hamiltonian and ux, and then when you apply uz, it gives you a different state because it changes the value of ux. So you get two degenerate states. But on the other end, in the phase where they commute with each other, you can have singlets. And actually, the reason why you have any doublets at all is because you still have a full continuous symmetry around the z-axis. But if you just had these discrete 180-degree symmetries, this would split up completely. So let's see what I... Yeah, so that's a way to see that these two phases are different. And it turns out you can actually argue that any two phases, that this is the only difference that you can have between phases. So for one, if you didn't have any symmetry at all, every one-dimensional phase is equivalent to every other one-dimensional phase. And if you do have symmetry, the only thing that you need to know about the symmetry is how these phase factors appear. So that's like different than like the kind of topological order that Chetan was talking about, because that topological order, you don't have to have any symmetries. There's some kind of fancy entanglement that you can have in two dimensions that you can't have in one dimension, and that's why it's possible. So I'd just say one other thing, which is sort of the physical interpretation of this. So it's a little bit of a backward order, but like the neat interpretation of this is that if you would just look at the wave function on a finite chain and look at the physical ends of the chain, there's also a double degeneracy at the ends of the chain. And what that means is, like if you have a spin one, this is for a spin one chain. If you don't have this anisotropy term, those doublets represent like sort of effective spin a halves at the end of the chain. Like you have a system made out of spin ones, but at the ends it seems as if there's a spin a half. So it's sort of an example of fractionalization, kind of similar to how a topological insulator has only modes going in one direction at the edge and not the other direction. Here you have like half of a spin. And that's something that people have seen experimentally. Like there's a material which is, I know that, I think I never knew the actual, it's called NENP. And it has a bunch of like organic stuff in it, and then there's the nickel atoms, which are the spin ones. And then you put impurities in it, so you get a spin chain made out of spin ones. And then you put copper impurities in it that break the spin chain up into short segments. And each time it breaks up, you get a spin a half on each side. And then you can do like electron spin resonance and see that there's doublets from those ends. About the entanglement? Yeah, so if you look, so this property, you could think of this as like a way to classify the state, sort of just by looking at the ends. But it's not, it's like, you like to find a way, or I'll say it in a more general way. Like if you think about topological insulators, for example, the way that you can describe them is by looking at the surface states. But for that, you need a finite system. So it would be nice to see that there's something in the bulk that tells you you have a topological insulator. So and also in the ground state. So what you can do is you can take an infinite topological insulator and then divide it into halves, and then you see in it measure the entanglement spectrum. And then the spectrum of the entanglement Hamiltonian, like if you have a quantum Hall insulator, the spectrum of the entanglement Hamiltonian looks just like the physical edge spectrum, except that it's even neater because the entanglement spectrum is really one-dimensional. Like the low energy modes are all restricted near the boundary. So the entanglement spectrum basically keeps going up. You have this is your Brillouin zone. It goes up and then it wraps back to the Brillouin zone and it keeps going up. So from looking in the bulk, you see this pattern, and that tells you that you have a topological phase. And the reason why the bulk entanglement spectrum looks similar to the surface spectrum is because like you have only certain degrees of freedom on the bulk. You're only allowed to use the degrees of freedom on the bulk because of the gap growing as you go away from the surface. And from those degrees of freedom, you can only make a chiral mode. Like once you have a chiral mode, you can't get rid of it except by taking a mode that goes in the opposite direction. So if you have only one surface, you have to get these fractional modes. So this is sort of a one-dimensional version of that. Like at the edge, you have a spin a half. And that means that in the entanglement spectrum, actually every single state of the Schmidt spectrum is half integer spins. So if you had full SU2 symmetry, you'd have some spin 1/2 multiplets and some spin 3/2 and some spin 5/2, but you never have integer spins. Oh. Yeah. Yeah. I mean, I think in terms of if you write the entanglement Hamiltonian in terms of effective spins, the U's would just look like rotation, like an ordinary spin rotation. Yep. Mm-hmm. Yeah. Yeah, like the Majorana states. So that you can understand it basically in this way. Because you can say, like say you have a system with fermions. Then you have the fermion number has to be conserved mod 2 at least. So you have like Q is fermion number mod 2. So like for a bosonic system, a single symmetry wouldn't give you any like non-trivial phases because you don't have anything to commute it with. But for the fermions, you have a simpler way to classify. So you try to factor Q into a left end and a right end, and then those ends might be fermionic operators, and that would be the non-trivial phase. So you just factor Q, and if the factors change the fermion number, then you have a non-trivial phase, and if they don't change the fermion number, then you have the trivial phase. Well, I mean, you could say it's not a symmetry that protects it because it's a required symmetry. It's not like, yeah. But I mean, you can derive it from that fermion parity. But there's still a difference between fermions and bosons, because if you had bosons with a Z2 symmetry, there wouldn't be any phases. So there's an extra thing that happens when you have a fermionic system, which is that you can have fermionic operators. So these are sort of like the Majoranas at the ends. You have operators at the two ends that anti-commute with each other, but they don't change the energy, which you can construct by factoring this two operator. Yeah, well, you would just see the lowest state would be double, and then you probably have a continuum for that. Yeah, the entanglement never gets to a continuum because it's one dimension less than the physical system. So it's like effectively a zero-dimensional system, which means at discrete level. I mean, the physical system might have a few levels before you get to the continuum, and each one of them would have to be like spin a half. But in the entanglement spectrum, you just have infinitely many levels, and they're all half integers. Yeah. Oh, in this case, yeah, because in this case, the symmetry of the original Hamiltonian, it had the extra rotational symmetry. And like if you have it had continuous rotational symmetry around the z-axis, and then you can have degeneracies even without like those special phases. Because like you basically have angular momentum. You have states that have an angular momentum plus m, and they're degenerate with states that have an angular momentum minus m. So like if m is the angular momentum around the z-axis, if m is 0, it's a single state, and if m is not 0, it's a doublet state. But yeah, that's sort of a confusing. So, but a good point is that I can make from that is, just from looking at the spectrum, you might not actually be able to tell that it's which topological phase it's in. Like you might have two different phases that both have doublets. If you really want to figure it out, you have to calculate these U matrices and then take the commutator. Just the energy, just the degeneracies don't immediately tell you what the phase is. Maybe we can go to eating. We can go, whoever gets there first can get the cheesecake. What? Oh, where are you?